We're just going to work a few more logistic growth examples, and that'll give us a better idea of how to manipulate this function into the form that we need for logistic growth. dp dt equals little k times p times the limiting factor 1 minus p over big K. So a population of polar bears is represented by the logistic differential equation where t is measured in years. So we have dp dt equals 0.08p minus 0.00004 p squared. Find little k and big K, the carrying capacity. So you have to do this oftentimes on the AP, so we need to be able to manipulate from this form into this form, and that's just algebra, but believe it or not, it can get a little intensive sometimes. I like to, you may have a completely different way for you to do it, and if you do, knock yourself out. I like to go ahead and turn things into fractions. We have 1, 2, 3, 4, 5 zeros here, so 100 thousandths p squared. I am going to simplify things. There's a 4 up top and a 4 down there that will cancel. And there's a 4 up top and a 4 down there that will cancel. Again, all of this is just algebra. I recognize now that I need to factor out from both of these terms 2/25ths p. That's going to leave me a 1, and then it's hopefully going to leave me p over something, and that something's going to be big K. But right now I can tell that little k is going to be 2/25ths. So let's see here. Algebraically, 2/25ths times 1 over something is going to have to equal 1 over 25,000. So I recognize there's going to be 1,000 down here, but I've got to take care of this 2 as well. So that's actually going to be 2,000. So our carrying capacity, big K, is 2,000. And that just takes some practice. You may have a completely different way that you want to do it. I like to do it where there's not a calculator present because many times we're going to encounter logistic growth where a calculator isn't present. So you need to make sure you can do that without the calculator there to help you. All right, the growth rate of a population P of bears in a newly established wildlife preserve is modeled by the differential equation dp dt equals 0.008p times the quantity 100 minus p, where t is measured in years. What is the carrying capacity for bears in this wildlife preserve? Well, again, not shockingly, we're going to find ourselves doing this a lot. We're going to have to get this into the form where we have a factor that's 1 minus p over big K. We're asked to find the carrying capacity a lot. So we're going to have to factor a 100 out here. So we're going to have 100 times this, and then if we distributed 100 back through 1 minus p over something, how would we get 1 for an answer, right? Because that's basically what's here is 1 as far as a coefficient to p. So we would, and that 1 doesn't need to be in there, sorry, 100 times p over what equals 1. And so that would be 100, okay? 100 times 1 over what equals 1. So that's 100, because technically that equals p. I'm getting tired, y'all. All right, so there's our carrying capacity, okay? Big K is 100. What is the bear population when the population is growing the fastest? Remember, it is always half the carrying capacity. What is the rate of change of the population when it is growing fastest? So what is dp dt, and I'll go back up here to this form of it, when p equals 50. And so that's all we're going to do is just plug in p equal 50, and we're not going to, even take time to clean it up, but there's the answer to that. So these are not terribly difficult questions, and they sound a whole lot alike. You're going to get asked the same things over and over and over again. So for each equation, find the carrying capacity of the population, so find big K. Find the size of the population when it's growing fastest, that's always going to be half of big K. And find the limit as t approaches infinity of the population. Well, shockingly, that's going to be big K. See how much carrying capacity comes into it? So again, all we're going to have to do is just put these into the form of our logistic growth model. So this is something, obviously, in this context, you have to be able to pull up immediately. So dp dt equals, and I'm going to factor a 200 out front, 0.006p, and that's going to leave me 1 minus p over what? And we saw in that last example that that's going to be over 200. And we can check that. If we distributed that 200 back through here, we would have 200 minus p. So our carrying capacity is 200. It's growing fastest at half the carrying capacity, that's 100. And the limit as t approaches infinity for this population is the carrying capacity. So again, sometimes if it's in this form, you can recognize that actually there's your carrying capacity, and you don't have to do all of that work. So here we'll just cut right to the chase and say the carrying capacity is 700. It's growing fastest at half the carrying capacity, that's a population of 350, and the limit as t approaches infinity of our population is the carrying capacity 700. Okay, and we'll work one final example here, which is a little bit different. Given a solution for the logistic growth model of P equals K, so the carrying capacity, over the quantity 1 plus the initial population times e to the negative little k, and that little k is the same one that shows up in the logistic growth model, times t. Now, instead of us trying to separate and integrate and come up with the actual p of t population function, it's being given to us. All right, so this is just formally given to us. This is one logistic growth model solution where P naught is the initial population, T is measured in years. Find the current population, find P after 23 years. So when T is 23, with an initial population of 2. So the only thing that we don't have here to plug into this formula is we don't have little k and we don't have carrying capacity. All right, so again, we need to change dp dt, that's 0.006p. We need to factor that 200 out front, so it's 200 times that, 1 minus p over 200. So now we have all the players because 200 times 0.006 is actually little k, and we can see big K is 200. So now it's just a matter of plugging those values in to find what this population is. It's the carrying capacity over 1 plus the initial population times e to the negative little k, which is 200 times 0.006 times t, which is 23. And we wouldn't have to clean that up. And finally, we'll do this one final example. So dp dt here is, we'll factor our 700 out front times 0.1, 2, 3 zeros and an 8, p times 1 minus p over 700. Okay, so again, p of 23 for this population is 700, the carrying capacity, over 1 plus the initial population. It says for both of them the initial population was 2. E to the negative, now this is 700 times 0.123 zeros and an 8 times 23. All right, So you can see, again, I know I've said it over and over, but this is not a terribly challenging concept. It's just kind of foreign to what we've been doing, and a lot of it deals with us being able to identify the carrying capacity and talk about what that means for the population under a logistic growth model. So there is our logistic growth model continued work. So come to class next time. We'll do some more logistic homework, and we'll be set to go.